Okay, so today I'm going to tell you about elementary and piecewise elementary functions. So, elementary functions include almost all of the functions that we're ever going to talk about. Almost all of them. Elementary functions include many of the types of functions that we've talked about already. It includes the algebraic functions, which, if you recall, includes both polynomials and roots. It includes all the trig functions, any kind of exponential functions, inverse trig functions, and log functions. All of these fall under the umbrella of what we call elementary functions. But not just that. Elementary functions include many of the ways that you could combine these with each other. So, down here I have some ways that you can combine elementary functions to make new elementary functions. Like if I can take two elementary functions and add them together, and that's considered elementary, or subtract them. I can multiply them together, I can divide them, I can do f of g of x or g of f of x or function composition, and these are all considered elementary functions. So, for example, I can take a trig function plus a root, because trig functions are elementary and root functions are elementary, so I can add them together and get an elementary function. I can take an inverse trig function of a root, like I can do arctangent of the cube root of x, and that's elementary. I can do any kind of exponential, and it doesn't just have to be e to the x, it can be e to any elementary function that I want. Like I can do e to a polynomial like this one. I can divide it by any kind of logarithm I want, and again, it doesn't just have to be log of x, it can be log of a trig function or log of any of the things that are on this list. And, I wrote down, I went a little wild with this one, but I just want to show you that elementary functions really include many kinds of combinations, any kind of combination using these operations: addition, multiplication, division, function composition, meaning like f of g of x or g of f of x. You can combine elementary functions in any of those ways and get new elementary functions. So this kind of begs the question, what isn't an elementary function? Because as I just described elementary functions, it kind of seems like that includes everything we could ever imagine. But there's one specific thing that does not necessarily give you an elementary function, and that's when you do a piecewise function. So I'm going to define this really sort of formally, and then we're going to do examples. I'm sure you've all seen piecewise functions before, but maybe you haven't seen them described quite like this. So say we're given some functions, say f sub 1 of x all the way up to f sub k of x, and we have some intervals, and these are disjoint intervals, meaning they don't overlap. So I have some intervals I1, I2, up through I sub k. We can define a piecewise function, and it looks like this. You have like this curly bracket, and there's just a left bracket. There's never a matching right bracket when you do it this way. This is just the notation for how you define a piecewise function. I'm going to define this function f of x, and if x is inside this interval, then I'm going to use this function. If x is inside this other interval, then I'm going to use this other function. And so it just lists different intervals that x can be in and which function you use if x is in that interval. And that's how you evaluate f of x. You figure out which one of these intervals x is in, and then you plug it into that function, and that's how you figure out f of x. if all of these f1 through fk, like the functions that you see up here, if each one of these is elementary, then we're going to call f piecewise elementary. So this is an important distinction. I'm calling this piecewise elementary. It's not just plain elementary, or not necessarily. When you make a piecewise function out of pieces that are elementary, you don't necessarily get an elementary function. In other words, this is, roughly speaking, this is a way in which you can combine elementary functions, but it won't necessarily give you an elementary function. We went over all these ways that you can combine elementary functions and it will give you an elementary function, like you can add, multiply, divide, or plug them into each other. But this is a way where you can, even if each one of these is elementary, when you make the piecewise function out of them, the result is not necessarily elementary. It is, however, what we call piecewise elementary. Anyway, let's start with a simple sketching the graph of a piecewise function. So there's just two lines here, and the intervals are described in terms of inequalities. Of course, this says x less than or equal to 1. I could rewrite this as an interval, like this would be the interval from -infinity to 1, including 1. It's not written as an interval, but this inequality really tells you an interval, so it's like the same thing. Similarly here, this inequality is basically describing an interval. So that's not a big difference from how I described it. But let's talk about how to graph such a thing. Here's what I would suggest. I'm going to start just by graphing 2x minus 1 all by itself. And then I'm also going to graph the other one all by itself. And these are just lines. So this has a y-intercept of -1 and a slope of 2. So this looks something like this. This one, actually let me write -x plus 2 just because, you know, it's more sort of standard form. It has a y-intercept of 2 and a slope of -1. So kind of like that. Now that I've drawn each one of these, I'll draw the piecewise function. So I'm writing y equals f of x just so I know that this one's the real thing. This is going to be my final answer. And what you do is we're just sort of going to kind of like chop off pieces of that. Like I'll chop off a piece of this graph and chop off a piece of that graph, and I'll put the two pieces together. So how does this work? I'm going to take the piece of the first graph where x is less than or equal to 1. So if it helps, sometimes I like to draw a little dotted line where I'm cutting it off, and I'm taking the piece to the left, like because x is less than or equal to -1. And then for the second graph, I'm going to take the piece for x greater than 1. So I can sort of draw a line here at x equals 1. And I'm going to take the piece to the right of that. So I'm going to take this piece here and this piece here and put them together. So, okay, so it's important to get like when you're trying. So, okay, once again, I am not a world's famous artist. Um, However, I'm going to put in some effort to get a few things right. One thing that's important to me is getting the transition point right. So when I draw this, I'm going to specifically look at the point where this gets cut off. So I'm looking at this point. So this is the point 1, 1. And then just to make sure I draw an accurate line, let me also get this point. Yeah, and I drew a closed dot here. Sometimes when you're graphing a piecewise function, you draw an open dot, and we'll get to an example like that later. But it's a closed dot because this is x is less than or equal to 1 here. Okay, so this is my first piece. What's my second piece? My second piece is this one. And again, I want to get the transition point right. And in this one, we have kind of a coincidence because this point is the same as this point. In other words, when I draw this piece, it's kind of picking up where the last one left off. So it goes through this point. It also goes through this point because it has a slope of -1. And it just goes like this. Now, normally, let me explain something. Normally, I would draw an open dot here because this is x is strictly greater than 1, meaning that it's not including 1. However, this point was already filled in from the previous part because from the previous part, this happens to be the same point and there's a closed dot there. So this is my graph. Let's do a slightly more complicated one. This one has 4 lines. I'm just going to go about this pretty much the same way, though. I'm going to graph each one of these. The first one is just y equals x. We all know what that looks like. Next, we have y equals x squared. Something like this. Then we have 3. So this seems a little weird, but I'm just going to do it. Y equals 3, that's just a horizontal line, right? That's just this line. And then finally, y equals e to the x. We've seen that graph before. So exponential graphs, they all go through this point. Okay, and let me get a new piece of paper because I don't want to draw this one too small. So my final graph is just going to be made up of like the chopped up pieces of these 4 graphs. I just have to, and yeah, so maybe I can draw my dotted lines now. The first one is for x less than -1. So here's a line at x equals -1. And so I'm going to take this part of this graph. The next one goes from -1 to 0. So I've got like a line here and a line here. And so I'm taking this part of this graph. The next one is really just for x equals 0. So it's like okay, so this is going to look funny, but this is like I'm circling a single point. I'm just circling the point where x equals 0. You'll see what happens with this when I draw the graph. I admit that looks a little funny right now. And then the last one is for x greater than or equal to 0, so I cut it off here, and I'm taking this part of this graph. So my final graph, I just have to put this all together. This piece together with this single point, and then this piece. And we also have to be a little bit careful about where do our open dots go and where do our closed dots go. All right, let's do this. So first, I've got this part. This goes up to -1, but it doesn't include -1. So I'm going to draw this much of the line, but I'm going to draw an open dot here. So here goes open dot here. And I'm going to try to make an effort to get the line right, because this line has a slope of 1, so I want to kind of make it look like it does. Okay, so I'm satisfied with that part. Now what? Now I wanted to take this piece of this graph. Looking back up here, this part includes x equals -1, but not x equals 0. In other words, I'm going to have a closed dot here and an open dot here. Something like that. And notice that these two pieces really didn't line up. Like, this one sort of left us off at this point, and this one, the next piece, just jumped directly up and started here instead of here. That often happens with piecewise functions. It's actually kind of a coincidence when you have it like on the last example that we did, where the two pieces actually lined up at the same point. It's typical that you'll see stuff more like this. Okay, now what? Now we're here, and we just wanted to do this single point. And that's actually easy. That's, let me find the point. This is the point 0, 3. I'm going to put a closed dot there, because of course that's included. This includes x equals 0. In fact, that's the only thing it includes. So this is definitely a closed dot at x equals 0 and y equals 3. So I draw that. And then finally, I'm at the last part. The last part is for, whoops, actually, what I wrote here wouldn't have made sense. Let me make that greater than 0. It wouldn't make sense greater than or equal to 0, because this one already included 0. And then you shouldn't have two intervals that both include the same thing. So sorry about that. This should have said greater than 0. Meaning that I'm going to take this part of the graph with an open dot there. And this is the point 0, 1. And remember, it's important to me to get the transition points right. So that's this point. And then other than that, I'm just going to kind of make a shape like this. So that's my graph. Yeah, so let me just point a couple of things out. This is a function, of course. If we've been calling it a function, it is one. And I just want to point out that the graph does pass the vertical line test. Anywhere I draw a vertical line, it crosses only once. There may be a couple of points where you get suspicious, like if I draw this vertical line, it goes through here and here, but keep in mind, this is an actual point on the graph, and this one isn't. That's the point of making a closed dot or an open dot, is to indicate whether there's an actual point there. Also, this vertical line only goes through one actual point on the graph. It goes through two open dots, but those don't count for anything. What counts is this one, and then so this vertical line really only crosses the graph once. Okay, so maybe that's it for today.